So in order to talk about three-dimensional moments, we have to introduce a type of vector multiplication called a cross product. In the next lecture, we'll actually talk about a dot product, which is a different type of vector multiplication. We'll get to that on the next time. But cross product, we take two vectors, for example, the A vector and the B vector shown here, and we cross them together to get a C vector in a direction that's perpendicular to both A and B. Okay, so again, the A vector and the B vector are separated by an angle theta. Okay, so the magnitude of the C vector, okay, this vector going straight up in this picture, is simply the magnitude of A times the magnitude of B times the sine of the angle theta. Okay, and that's the definition of the magnitude of a cross product. Okay, now the tricky part about a cross product is this idea of what direction that C vector is in. Okay, and I alluded to this earlier. We use the right-hand rule. Okay, and what you do is you start by pointing your fingers in the direction of A, and then you close your hand, curling your fingers towards the B vector. Now, the direction that your thumb is pointing in is the direction that C is in. So if you think about, again, that and this would be like a rotation vector, like the moment vector, which we're going to be getting to and why we're doing this whole cross product to begin with. Okay, so we have A cross B. So you point your fingers on the right hand along the A vector, curl them, close them towards the B vector, and your thumb points in what we call the C vector, and that C vector is going to be perpendicular to both A and B, so perpendicular to the plane that A and B lie in. Okay, now, unlike the cumulative law for multiplication, where, for example, 2 times 3 is the same thing as 3 times 2, the cross product, because of this right-hand rule direction that I've got here, A cross B is actually negative B cross A. Because if you think about taking that right hand and starting with your fingers pointing along the B vector and curling those right-handed fingers towards the A vector, your thumb is actually going to point downward in the opposite direction from what we did earlier. So A cross B actually equals negative B cross A. Okay, so keep that in mind. The order of this cross product is very, very important. Otherwise, you're going to be getting negative answers when you take these cross products. Okay, so we do this for Cartesian vectors. Okay, so I've got a couple of pictures over here. Here are your unit vectors, right? I, J, K. Remember how I talked about that your X, Y, and Z axis always have to be in this orientation. Okay, that's because of this relationship right here. Okay, by definition, our sign convention is that I cross J equals K, and really that's the only cross product I want you to memorize, is that I cross J gives you a positive K, which means that if I point my fingers along the I vector, close them, curling them towards the J vector, my thumb points in the K direction, or the Z direction. Okay, so if I have two Cartesian vectors, such as AX times I plus AY times J plus AZ times K, and the same thing in the B, okay, what I do is for each one of those, so I take I cross I, right, AXI cross BXI, well, I is in the same direction. Okay, that would mean that my theta is 0. So all of the like components, if two vectors are pointing in the same direction, okay, the cross product of those is 0. So you'll notice that as I go through this, there's no AX times BX, AY times BY, or AZ times BZ, because again, those vectors point in the same direction, meaning that the angle between them is 0, so they have no magnitude. Okay, so I'm only concerned with those cross products, okay, or those vectors. So I cross j, j cross I, k cross j, these sorts of things. Okay. Now I can do a right-hand rule on each one of those, and just to speed things up a little bit, we can talk about this when we actually go through in class and solve them. Okay. You can do each component. So I cross j gives you a positive k. So that would essentially be this vector right here, right? Ax cross by in the j gives you a positive k. So conversely, j cross I, remember, because of this negative sign, gives me a negative k. Or I could take my right hand, go from j to I, and my thumb will point down in the negative k direction. Right? So what I have here is j cross k gives me a positive I. So again, if I put my right fingers in the j, curl them up towards the k vector, my thumb is going to point in that x direction, or that I direction. And then the converse of that is going to be negative. Okay, notice this negative sign. So I cross j, or I'm sorry, excuse me, let me start that again. I cross k, I point my fingers and my right hand in the I direction, curl them up to the z-axis, my thumb actually points in the negative j direction. So this negative sign makes this negative j. That means k cross I is actually positive. Or you could point your thumbs k, I. Okay, so you can either do that with your right hand, or another trick is to use this sort of circle. If I move this way around the curve in a, as shown here, a counterclockwise manner, that's a positive. Okay, if I rotate in the clockwise manner, that'll be negative. So what I'm saying is, if I go this way around, so if I go I cross j, that's going to give me positive k. J cross k gives me positive I. K cross I gives me positive j. I'm going the opposite direction, right? J cross I equals negative k. I cross k equals negative j. K cross I. Okay. Now, these cross products take a long time to do. Okay. Because you have to go through and do, each I cross j and k cross I and j cross k and what have you. Okay, and kind of doing that FOIL method with your equation here. Okay, this is why we started with 2 dimensions, so you could see how moments work before we get bogged down with this whole idea of a cross product. Okay, now if you are familiar with determinants, okay, you can just take the determinant of this matrix to solve for the cross product. Okay. So if you know how a determinant works, you would take this, the I vector, and you would do the, kind of make that x. So AYBZ minus AZBY times the I vector. That's what I have here. J, you got to put the negative out in front of it, but then it's AX times BZ minus AZ times BX. Okay? And then I go to the K, back to a positive on the k. This is just how determinants work. I would go ax times by minus ay times bx. So you can always go through that determinant as well. Your calculator will solve this as well. Okay. So don't really memorize these equations. Just with practice, the cross products will become very easy. We will go through this in class. It'll be much easier because I can actually show you how my hands go and whatnot. So that's how the cross product generally works. Okay. Now we use this to determine the moment of a force. Okay. So the definition of a moment of force is just the r, that would be the moment arm, crossed with the force vector. So r would be from the point to the force. And again, it can go from the point to anywhere along the line of action of the force. Okay, so I go R cross F, which means I point my right hand fingers. Well, we'll get to the direction in just a second. First, the magnitude, again, just going to be R times F times the sine of theta, where theta is the angle between R and F. Now, if you think about drawing that perpendicular line, which is really, really hard to visualize and do in 3 dimensions. So we typically do this cross product, but if you were able to draw that perpendicular distance, FD, recognize that that's opposite of theta here. So R sine theta times F is the same thing as the magnitude we got from the cross product previously. Okay, so it's the same idea. You can solve 2D problems using the cross product. I find it easier just break them up into perpendicular components and solve it that way. Okay, so the magnitude of this is just RF sine theta. Okay, more times than not, we'll just be doing the full cross product, but just show you how they're related. Okay, and the direction is going to be perpendicular to the plane that contains R and F. Okay, following the right-hand rule. So again, it's R cross F, not F cross R. That'll give me a negative answer. R cross F. So I point my right-hand fingers in the R direction, and I curl them, close them in on F. Okay? And in order to do that, my thumb needs to point up. That means I've got a rotation about this, what we call moment axis. Like so if I'm taking the moment about, if you think about force going this way, that's creating a rotation about this axis. Just like I've shown here, following the right-hand rule tells me what direction that moment is in, pointing my fingers. And remember, this is a rotational vector, so it's not that it's pointing in that direction, it's rotating around that axis that's pointing in that direction.